EAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede 5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
This session is going to be on stability and control of an airplane. It is a fairly important and fairly critical subject that has to be covered. When you're designing an airplane, it's important to have adequate stability of the airplane on all three axes. At the same time, you don't want so much stability that you don't have control over it. That's the key thing, is to come up with a balance between adequate amount of stability, no more than you need, but enough, and adequate control to basically upset this stability and be able to maneuver the airplane into the flight condition and flight regime that you want it to be in. There are basically two types of stability that have to be concerned with. One is static stability. This is the actual basic stability of if the airplane's flying along and a gust of wind pitches the nose up, will the nose come back down? If that's the case, that's considered positive static stability. Dynamic stability is another factor. In some cases critical, but in most cases not quite as important as static stability. And dynamic stability is if you're flying along, a gust hits you, lifts the nose up, the airplane will come back down, but how far will it go? Will it go too far? And if it does, how will it gradually, through dynamic conditions, restore itself? That kind of condition also should be looked at. When we're dealing with static stability, we have to worry about longitudinal stability of the airplane in pitch, this condition. We want lateral stability, condition in roll, and of course we want directional stability, condition in yaw. All three axes have to be looked at, have to be understood. Some are more sensitive than others, some are more critical than others. Directional stability, for example, is pretty easy to obtain by an adequate fin rudder area. It's almost impossible to have too much directional stability. When you evaluate flying qualities and have different pilots fly different type of airplanes, no one ever complains about the airplane being too stable in directional pitch control. But you still need an adequate rudder to overcome this, because there are times you do want to yaw the airplane. When it comes to roll stability, you need a modest amount. You want it to be able to fly along, and if a gust lifts the wing, you want the wing to be able to level back out again. Model airplanes, the little free flights where you start up the engine and let it go, you must have a great deal so that the airplane will maintain a condition of not going off into a spiral. But that kind of stability is actually excessive for normal operation in an airplane flying along. So roll stability should be there, but not too much of it. Your ailerons fundamentally are the controls that you use to counteract that. The right amount is not that difficult to obtain. The right amount of stability is not that difficult to obtain. The type of controls, the type of ladder controls, on the other hand, is a little bit more critical. In most cases, it's not too hard to get a control to work under some of the conditions that the airplane flies through. The trick is to be able to get it to operate under all conditions: high speed, medium speeds, low speeds, and right up into stall. And the best part, if you can do that, is not just have the control, but to have the control response and the forces within the stick to be nice and equal and even. The final one is pitch stability, longitudinal stability, and that is a lot more complicated and a lot more difficult to obtain. You have a center of gravity, travel, and a few other factors that are into it that are somewhat difficult. What we want to do in this session here is not get into the specific equations and the specific numbers of evaluating stability and control, because there are number of books out that will give you that. Probably one of the very best ones is called Airplane Performance, Stability and Control, and it's by Perkins and Haig. I'll give you a little bit more information about this, but this is probably one of the very, very best textbooks that are around that gives good detailed engineering analysis as how to determine stability and control all of the factors that affect static stability, dynamic stability, and control about all three axes. There is also another NASA report that was done in 1949. It's called TR 927, and the title of that particular paper is called Application and Prediction of Flying Qualities. This deals primarily with stability and control, but it carries it into the area that you're finally interested in. What are the flying qualities of an airplane? How does an airplane actually handle? We jump in an automobile, we start driving down the street, we turn the wheel. We don't really give too much care as to what it is. What we want to make sure is that that wheel has the right kind of force on it. If the wheel had power steering and power steering was too great, it would just over-control itself, you would not like to drive that car at all. If the force in turning the wheel was so heavy you could barely move it, you wouldn't like that either. You'd say it drives like a truck or something. So you want a nice balance in there. In an automobile, it's a relatively simple thing. In an airplane, you got all three axes, and you got these variations of speed, and you got the dynamic conditions. So flying quality is the term used to summarize all of that. What we'd like to do in these tapes is to discuss the characteristics and the things you have to worry about in taking up these stability factors and trying to fill in the space between what you'll find in the textbooks and what you'll actually find when you get into flight test work on your airplane. I think it's real important that we take a look at longitudinal stability, talk about that the most, because it's the one that's the most sensitive, the most critical to be concerned about. And if you're a pilot, you probably know real well that the tail on the airplane is the thing that gives you your stability, and that basically that's the case. If it's a flying wing, you obviously have no tail, so therefore you must shape the wing and the airfoil section so it gives you stability automatically. But there's a big variation that goes in there in between that, and there's a lot of other factors that enter into it. But surprising enough, as I talk to pilots and even other engineers, how they really have a difficult time in understanding precisely what does give you the stability that you're looking for, particularly longitudinal stability. Let's take a look at a basic configuration of an airplane having two surfaces, a front surface and a rear surface. Whether this is a conventional aircraft with a large front wing and a small tail in the back, or actually a canard with a small tail up front and a large one in the back, fundamentally everything is identical. But in this particular case, let's start off by saying we have two wings here of the same chord, same wingspan, same aspect ratio, same size, two identical wings, and they're both connected together with a little fuselage at the same angle of attack. If we were flying along at a 2-degree angle of attack right here, and in this case, let's forget the downwash off the front surface on the back one, just to keep everything simple. So we could say the back one, sitting at the same incidence, has the identical angle of attack. Well, in that case, the lift generated from this wing at quarter chord would be the identical that the back one is lifting. Both would be the same. Well, if that is the case, we want to balance the airplane out halfway between this point. So if this is X, this would have to be X. We would put our center of gravity, we would hang our weight here. If this is L for the amount of lift, this is the same amount of lift there, this would be 2L. Everything's balanced. This airplane would fly along real fine, except for one thing. If it happens to hit a gust of wind, and the angle of attack here went to 4 degrees, this lift might double, this one would double. The total amount that it could lift would be twice as much now, but it would still be balanced, and it would still stay at 4 degrees, or 6, or whatever it is. It would be balanced, statically balanced, but it's not stable. It'd be neutrally stable. That isn't what we want. We want it so that when it's flying along at 2 degrees, it hits a gust of air, the airplane will then return back to the 2 degrees. That's what we would define as laterally stable, or longitudinally stable, and that's the objective we'd be looking for. How do we obtain that? Well, let's assume now that we take this wing back here, and we reduce the incidence of it. I'm going to exaggerate a little bit on the board here just so you get a better indication of the difference between the two. And let's assume that we actually put this at a 0 degree of incidence compared to this one. Now when we're flying along, we have a 2 degree angle of attack on the front one and a 0 degree angle of attack on the back one. Well, let's take a look at a CL versus alpha chart. This is particular one that happens to be for 4415 airfoil. What we can see here is this. Let's take a look at this particular problem. At 2 degrees angle of attack, we would be generating a CL of 0.6. All right, let's take a look at that. If we had a alpha of 2 degrees, and that will be generating a CL of 0.6. This will be for the front wing. Then for the rear wing, we're going to have an alpha of 0 degrees and generating a CL of 0.4. Well, now, these surfaces up here will be generating a CL of 0.6. This one now will be 2/3 of that at a CL of 0.4. And of course, now that the rear wing is lifting less than the forward wing, we will not be able to have the CG in the center between these two aerodynamic center. It has to be moved further forward to be balanced. So now we will have the weight of the aircraft here. And let's just keep it down into something simple. Let's assume we have 10 units here from the distance from the CG to the quarter of that. For this one being only 0.4 compared to that one, this has to be 15 units. So now we have a situation here where 10 times the 0.6 is balanced equal to 15 times the 0.4. So we're statically balanced flying along at 2 degrees. 2 degree angle of attack here, 0 degree angle of attack here, generating 0.6 here, generating only 0.4 here. And yet we're balanced. All right, now we're flying along and we hit a gust of air. And we now go to 4 degrees angle of attack here and 2 degrees angle of attack in the rear. Well, what is that going to mean? That means for the front section, the alpha now will be 4 degrees. Okay. At 4 degrees here, our CL is 0.8. The CL is equal to 0.8. On the rear wing, we're going to have an alpha of 2 degrees. And of course, 2 degrees will develop us a CL of 0.6. Well, now you see what happens. This wing, and let me use colored chalk to show what happens after the gust. This wing will go on up to generating a 0.8 CL. This wing here will be generating a 0.6 CL. The CG obviously is stuck in the same place. Now you can see that 10 units times a 0.8 is not as much as 15 units times a 0.6. This has gone from 4 to 6. That's a 50% increase. This has only gone from 6 to 8. It's less than 50% increase. Therefore, the moment, the twisting action in the back here is greater, and the airplane is not statically balanced, and the airplane will pitch over and stabilize itself until it comes back to a 2 degree angle of attack. That's the fundamental thing about static stability of any kind of an airplane. What you really have to have is a balance between the front surface and the rear surface in such a manner that the rear surface, because it is at a lower incidence, will have a lower angle of attack. It will generate a relative or a percentage of increase of lift with the same change of angle of attack of the two surfaces that is greater. If we take a look at the model airplane, we can see essentially this. We're flying along at 2 degrees angle of attack. We hit a gust that makes it go to 4 degrees. But the relative moment arm of this tail, being back here, is greater because this increased to quite a bit. Now, in fact, you could go so far as to say, let's have the wing flying along and the tail at an angle of attack that is producing no lift on it, none whatsoever. Well, now the balance point has to be right under the quarter of the wing. And in that case, it's very easy to see that if the weight is totally under there, the rear section is lifting nothing, but soon as it gets any form of a change of angle of attack, whether up or down, it will immediately try and restore the wing up or down in the same particular way. If we actually made this wing smaller now, so it didn't have the same amount of area as we had in the beginning here, where the two were tandem wings identical, then we'd have to keep moving this further and further forward because this was a smaller total lifting force, and we had to do it until we were totally balanced. So that's really what it boils down to on any particular airplane. You have the front surface, which must be producing lift. You have a rear surface, which must be at a lower incidence, lower angle of attack, so that when a gust condition comes, its change is greater percentage-wise than the change in the front. A normal airplane, this is a large surface. This surface in the back here is relatively small. In fact, on most airplanes, what you have is a situation, because the camber of the wing, you actually have a download on the tail. The airplane is flying along, the wing is lifting, but the tail itself is producing a slight download. This is perfectly acceptable and perfectly good, because then when you get an increase in angle of attack, this download on here will get to such a case, if you hit a gust like this, in such a case that the download will reduce itself to where it has to change and pitch back over again. Now, if this is a canard airplane, it's all right. You've made this surface smaller and smaller, this one bigger and bigger. Your total lift on this one is very large, so therefore your balance point, your center of gravity, has to keep moving further and further back. But the same fundamental things must exist. When you're flying along and a gust hits you, this will increase in lift, this will increase in lift, but this one has to increase in a greater percentage of lift than the front one. This condition is somewhat sensitive for longitudinal stability, because what happens is, as we change the center of gravity, as we start to move this, you can see what effect this has to have on the loading on the tail. If we were to go back to this example again, where these two surfaces were identical, and we needed to, whatever reason why, we had to move the center of gravity further forward, well, immediately, to keep the airplane in balance, we would have to reduce the incidence of this. We'd have to let that same size wing as that one lift less than it does. And the further we move the thing forward, the more it would have to be reduced, down to the point where maybe it wouldn't be lifting at all if we moved it all the way forward, even though it's a very, very big surface. Well, you can see, as you moved it forward, you're making your tail become more and more powerful. That's why when a CG moves further forward on the airplane becomes more and more stable. As it moves further aft, the opposite starts to hold true, and eventually you can keep moving back to the point where you have neutral stability, even though the tail is of the same original size you had before. If we then take a good look at an airplane and try to understand all of the factors that are presented in here, we have directional stability, which is accomplished by the fin itself. The rudder is the surface that counteracts this directional stability, and again, we can have as much rudder as we would really want. The more we have, the more stable it is, the better a pilot likes it. But you also must have a rudder that's big enough to counteract it. Obviously, however, once you get into too big of a rudder, it has added more drag and more weight than you need. Unfortunately, I've made the same mistake, and other designers at times make a mistake. They tend to try to save a little drag and save a little weight by making small fins and small rudders. Frankly, that's a very small portion of the total drag. It's a streamlined surface. You could make it 20 or 30% bigger and barely pick up as much drag as possibly a poor landing gear design might do, or a bad exhaust system or something like that. So a good recommendation is don't get so doggone tight with trying to reduce the weight and reduce the drag of the airplane by cutting down on some of the surface area. Put a good fin, put a good rudder on it, and you can easily pick up what you gain in drag there. You can easily make that up by cleaning it up in some other areas. Okay, roll stability, fundamentally dihedral will give it to you. Obviously, the lower the center of gravity is, the more stable the airplane will be relative to the wing, and not only in roll but in pitch. But you can't really count too much on low center of gravities as being the primary form of stability. A lot of airplanes, they're low wings, and there your CG is above the wing regardless. So you can still obtain roll stability by putting adequate dihedral into it, or you can even sweep the wing, because the sweep in the wing will do, in effect, the same thing that dihedral will do. The shape of the fuselage will have a dihedral effect in it. again, Perkins and Haig's book covers these numbers pretty good. It's almost impossible to say what numbers should you use for dihedral. Should it be 2 degrees? Should it be 4 degrees? Should it be 6 degrees? It truly is a very difficult thing to calculate in the beginning. The coward's way out is build models of it, put in a wind tunnel, and get the exact numbers from it. But you can learn a little bit from experience from other airplanes and their characteristics. We all know that a low-wing airplane can operate with like a 4 degrees, 6 degrees dihedral, maybe even a little more. A high-wing airplane, 1 or 2 degrees dihedral. What happens if you have too much dihedral? Well, it gets very stable this way, but if you do not have exactly the proper aileron control, you're going to end up in a problem. What is the problem? Well, let's assume you happen to have a lot of dihedral on your airplane, so it's very stable this way. Now, you happen to also have ailerons that are big and chord and not real efficient. So when you go to roll the airplane, this aileron comes up and this one goes down. Now, this one going down will generate a lot more drag than this one going up. So it gives you adverse yaw, and the airplane skids through the air this way. If you have too much dihedral, you know what's going to happen? The dihedral is going to level you out again because you yawed to the nose to the right. So therefore, it's possible to actually take an airplane with a lot of dihedral, put ailerons on there that have a lot of adverse yaw, and as you try to bank the thing, you actually skid around. You actually cannot bank it. It sits there and waddles through the air in a very peculiar way. Now, if you have a lot of dihedral and you do not have adverse yaw, that the airplane would just bank very nicely on you, now you can counteract that with roll control, and then using the combination of the rudder and the banked airplane, you can make a reasonably decent turn. But it's not necessary to have a high degree of roll stability anyways. You want a modest amount, you want it to be comfortable, and most of the airplanes today with, say, as I was talking about, 4 or 5 degrees low wing, 2 or 3 degrees high wing, will give you a nice characteristic. There are some reports that talk about how to build in spiral stability, and that is a function of dihedral, length of the tail, and size of the tail. Because you want the airplane to be stable this way, but the dynamic end of it is going off into a spiral. And model airplanes are built so they have spiral stability. And most airplanes that we fly today are not spirally stable. If you take an airplane, put it into a bank, and let go of the controls, what will happen is it'll gradually tighten up on its turn and get into a real tight spiral. The time that's dangerous is if you happen to be in IFR conditions and you don't know how to fly IFR, and you're not watching the controls and the airplane starts hitting gusts, it will go off into a spiral, and you can come out of the clouds, unfortunately, not knowing which way you're turning if you don't have the right instruments or don't know how to fly them, and you'll be into a very tight spiral that can become very dangerous. So it's not a bad idea that if you can design into your airplane roll stability, but also the dynamic end of it, the spiral stability, and it's possible that actually can be done, or even neutral stability. The Bede 4 is a good example. You can take the Bede 4, fly along, put it into a bank, get it stabilized, take your hands off, and it'll stay there all day until you run out of gas. It'll just stay at the same bank angle no matter what happens. The trickier one, the one in pitch, you have a CG travel that you have to worry about. You have several other things. Your wing itself generally is an unstable wing. You have a little camber to it, or when you put your flaps down, it very definitely is unstable. So therefore, you use a tail to give you your stability. Look in the books, look at the numbers, take a good idea there. There's a thing called tail volume. This is just a rule of thumb. It's a relationship between the wing area, the wing span, the tail length, the distance from quarter chord to quarter chord of the tail, and that comes out to be a certain number. When that number relates to what other airplanes with tail volumes of equivalent type airplanes, then you know you can start off with an airplane that you know you have a reasonable degree of stability. Remember though, on longitudinal stability like this, you can increase the stability by moving the CG further forward. But as you move it further forward, your tail loads become higher and your stick forces. Now to maneuver the airplane, to change that position, you have to move the stick a lot more and the forces go up much higher. If you move it back, your stability go down, so does your maneuvering capabilities increase because your stick forces have gone down. The fuselage generally is destabilized, and unless you happen to have a configuration where there's very little bit of the fuselage sticking forward of the airplane and most of the fuselage in the back. But that can be calculated, that can be determined, but generally speaking, it is destabilizing. Don't forget about the propeller too. The propeller, when it's running, is invisible. You can't really see it to the eye, but it's there, and it's producing a load. And if a gust of wind hits on it, as it will when the airplane goes through a gust, it can become destabilizing if the propeller's in the front. It can become stabilizing if the propeller's in the rear. There's also an effect of whether the propeller's high or low, too, compared to the CG, because actually when a propeller is running through the air and it changes its angle of attack, the thrust line doesn't stay right on the shaft. It actually moves over and moves down a little. So the fact that it moves down affects the stability of an airplane, too. Those factors have to be taken into account if the airplane's horsepower, like a P-51 or something like that, where the horsepower is a great part of the whole airplane on it. But for a general aviation airplane with 150, 180 horsepower, the height position of the thrust line is really not too critical, but whether it's forward or back is somewhat. We have another situation you have to think about, and that is stick-free and stick-fix stability. When you're flying along with the airplane and you take your hands off of everything, feet and hands off, the rudder will just free float. It will just sit there, and if the airplane yaws, the rudder will just sort of trail along with it. When you're flying along, the ailerons will just sit there and float behind it. Your elevator will do the same thing. Now, if you hit a gust or something like that, ailerons won't move. They'll stay right there. They're locked into position. So roll stability is the same whether the stick is fixed or whether the stick is free to move. But the elevator and the rudder are different. If you're flying along and you hit a gust of air, the elevator will tend to float with whichever way the gust would be. So therefore you can see that if you were holding the stick and locked onto it real tight when you hit a gust of air, that's the same as having more tail area. So therefore stick fix stability is higher than stick free stability. And same thing with the rudder. If your feet are on the pedals and you're holding it tight and you hit gusts that try to move you, the fin and the rudder will work together and give you stability. But if your feet are off the rudder, it will tend to float with you. If you go to an all-flying tail, however, in the back, well, then you do not have a stabilizer elevated condition. It will not tend to float, and stick-free and stick-fixed stability in pitch is the same. And this is, of course, a real important thing to have. It's a real good thing to have, because pitch stability is a critical factor, and if you wanted to be able to be stable, a certain degree of stability with your hands off of it, with the ordinary elevator stabilizer, you're going to have a bigger surface area, because your stabilizer with a floating elevator now has to have enough power to stabilize the airplane as a smaller surface of an all-flying tail would do. So if you want the same degree of stability or you want the same CG travel, the all-flying tail is a real good thing to go with. There are a couple of key things you ought to be certain you understand when you're dealing with an all-flying tail. Let me go over to the board here and I'll show you just exactly what I'm talking about. It can be done other than using a symmetrical section, but it's strongly recommended that when you go to an all-flying tail, use a completely symmetrical airfoil section. Now, if it's a symmetrical section, whether it's a 4-digit, 5-digit, or 6 series airfoils, really won't make any difference. Your neutral and aerodynamic point will be right at quarter chord. And there is no pitching moments now. So, when you build a tail and you put your pivoting point right on a quarter chord, here is the airplane. Even though this is a beautiful biplane, imagine that this was an all-flying tail back in here. If you have it hooked up now to the stick and you're flying along and you hit a gust, since it is right on the quarter chord, that tail will not move. It'll stay right in the same position no matter how extreme you go. Obviously, if you go to the point where the tail will stall, then obviously something different. But say you stay within the normal range of stability on the surface, the loads will go up or down depending upon the angle of attack, but the surface itself, relative to the fuselage, drawing this as the fuselage in here, will stay the same. So that part's real good. So that means your airplane with your hands off is as if the tail's locked solid. But now you have this hooked up to your stick here and you go to move it. Well, you move the surface. Well, if you move it and you have the thing all at quarter chord, you're going to have absolutely no forces within the stick, because a symmetrical surface balanced on a quarter chord can go from 0 degrees to 5 degrees to 8 degrees to -2 degrees, and no hinge moments, no forces whatsoever on the thing. It's perfectly balanced all the time. So you don't like that. When you fly along, you pull back on a stick, you want to feel something. And when you push forward, you want to feel it the opposite way. The way to solve it is you put an anti-servo tab in the back. So you take this little surface back in here, and you put a little servo tab, and you hook it to the part of the structure. And what you want to do is have the ability so that when you change, and I'm exaggerating this thing a little bit here, you change the angle of attack or the incidence of the tail by moving the stick, you want a force that is generated to try to bring it back to its neutral point. So you make it so that the surface, this little servo tab or anti-servo tab, because the definition of a tab is this little surface in the back. If it helps you move, that's called a servo tab. If it fights your movement, then that's called an anti-servo tab. And in this particular case, that's what it would be. You normally do that by finding a spot somewhere above your quarter cord and hooking your structure to that. And so as it moved here, it will push this surface up. This is sort of one way of looking at it. And then as the tail came down, it would move the opposite. So now you have both. You have a surface that is perfectly balanced and stable by itself, so when it's flying through gusty air, the tail does not tend to move compared to the airplane, and therefore it acts always as a fixed surface and gives you your stability. But at the same time, when you do want to move it and you actually physically move the horizontal tail, your servo tabs, anti-servo tabs in the back, add the proper forces around the quarter cord, around the pivoting point, and give you the feel. What is sort of nice about this kind of design is that you can almost dial in the stick forces you want. If you want your stick to be real heavy, make your tab big, or make the cord of it big, or make the linkage such that it really moves the tab an awful lot. And boy, that surface will be heavy as can be. On the other hand, if you want it real light, you can change your linkage here, make them smaller, so the tab doesn't move very much, and that'll make it very, very light. And you can actually build the airplane and get it flying, and once you're flying, you say, wow, the elevator is too heavy. No problem at all. You go back there, almost drill different holes, and you can find new positions on your linkage and linkage alone and dial in the kind of stick force you want. This is the real nice part about an all-flying tail. But be sure that you put the pivot point on the quarter cord, and be sure that you end up with a symmetrical airfoil. It can be done with a cambered section, but you really end up with some tricky things, and you got to get into some very tricky details with it. One thing we did on a lot of our airplanes when we used an all-flying tail is we put a leading edge extension onto the thing. And let me show you a little bit about that. From a top view, let's assume this is the fuselage. And, well, let's take even the case of the Bede 4 where we had essentially a rectangular planform for the horizontal tail back there. We put the servo tab in this region in here. Now, everything's perfectly fine. Everything's balanced real nice. It pivots on the quarter cord, the servo tab, anti-servo tab that is, goes ahead and gives you the stick forces you want and everything else. But there's a couple things you have to be concerned about. Number one, it's balanced on quarter cord, but for flutter reasons, you want to make sure that it is statically balanced as far as weight goes. So you want the things to weigh in front of the balance point to weigh as much as the back part. Well, since 3/4 of your surface is behind your pivot point, there's no question about it, you're going to have to put lead up front. So you either put a bulge out here, you put some lead in there, or you can come internally and put a big bar up here and put your lead attached there, but you need some counterweights. The further forward you can go, the bigger the moment arm, the less lead you're going to have to use to counteract it, but it still has to be there. One of the ways we came up with it, though, is why not build little surfaces out here like this and put the lead on that. Now this did two things. One, it got us the lead further out from the leading edge. It put some on both surfaces so it balanced the thing so that it was torsionally pretty nice and stable. But most important, it gave us that aerodynamic characteristic of a little delta wing or swept wing surface in here. Why is that important? Well, if you have this all-flying tail and you get to a condition where you can pull the wheel back so far that you cause the tail to stall, and in most cases, this is when you're coming in for a landing, you pull back on the wheel, the tail starts to go down into this position. If it stalls on you, you got a real dangerous situation here, because what happens is this big download that you want to pull down on the tail now disappears. The tail is stalled, inverted, and it pitches up, and the nose comes down. I think a lot of you will remember that, about 10 years ago, Cessna with the Cardinal had this particular problem. They had an all-flying tail in the back, and they found out that when the airplane came in for a landing with the flaps down, everything was fine until they yawed it just a little bit. And if you've ever seen the movies of the flight test that they did thing with tufts on it, what was happening is there was a flow around the fuselage and the fin that came down almost vertically here. It was really quite steep right along the side of the fuselage, and it came down on his tail and caused the tail to stall. And there were some accidents, fortunately none that I heard that were serious, but a fellow would be coming in for a landing and everything else, and hit a little gust and yawed a little bit, and all of a sudden the tail stalled and the nose would pitch over and jam the nose right into the ground or something like that. So that's a little tricky. What they did to solve the problem is they put slats, fixed slats on the leading edge in here so that they could increase the angle of attack that the tail could tolerate, in this case upside down, but the principles are the same, and that prevented the tail from stalling at these extreme angles of attack. The delta wing surfaces for us, putting it out in here, did us the advantage in the fact that it caused a vortex to roll over the surface, which caused a nice vortex to build up on the tail back in here, and it kept the flow attached to this part of the surface. So the horizontal tail could never stall completely at any one time when you got to this extreme angle of attack. Maybe if you got very high and very excessive, the outboard section might stall, but a major portion of the tail still had energy to it, still was producing a download, and it was not any kind of severe reaction where the airplane would then pitch over very violently as the tail surface would stall. This has that advantage, again, that you can put your mass balance into it, you end up with a nice aerodynamic vortex to it, and then even from a side view, when you have this extended surface sticking out in here, from a stability standpoint in spin, this area up against the side of the fuselage is a very powerful area to giving you spin stability. So by doing this one aspect of the thing, we had 3 or 4 things that helped us out on it. It's a good method and a good effective way of doing it. You can make this go quite large if you want to, and make it close to the surface of the fuselage without any real problems whatsoever. Remember, however, to include this area when you're calculating the total area of this wing so you can determine your quarter chord to know where your hinge point should be. This type of configuration with this little delta wing surface is sort of the same thing you do on a fin and rudder when you put a dorsal fin on it. Let me erase this off and show you what I'm saying here. A fin and rudder on an airplane have a little bit different characteristics to it than what a normal airplane would have, or normal surfaces would have. When you're dealing with ailerons, when you're dealing with elevators, you're maneuvering, you're doing a series of things. In regards to the fin and rudder, primarily you want this airplane to fly straight through the air. You want this thing to give you directional stability. And when you do yaw, you're yawing under a controlled condition, a side slip kind of a condition, and you're being forced to fight this thing with the rudder by twisting the rudder in the direction to cause that surface to go over. So what can happen is, and let's take a look at it from a top view here. Here is your surface. If you want this thing to yaw and deflect the surface like this, you will then now start to twist the airplane over and it'll be flying through the air like that. So here's a peculiar airfoil. You can look at it just as if it's a wing with the flap deflected on it, and it's going through the air with this peculiar kind of angle of attack, you might say, to it. It's not like the normal wing flap configuration would be. It's cocked over and it's going through the air like that. If you go too far sometimes with this rudder, it will actually yaw the airplane so much that you get rudder lock. The rudder will literally snap over to the side. You don't really want to have that. I don't know of any general aviation airplanes like that, but back in the late 30s and the 40s, there were certain fighters that were built that way. If you'd sit there on it and yaw the thing an extreme amount, all of a sudden the rudder pedal would snap over in that direction. And you had to sit there and fight real hard on the other pedal to pull it back in. One way of solving that, or some of these other little problems, is put a dorsal fin on here. What is this dorsal fin going to do? When you yaw, you have this dorsal fin, it's going to make the vortex sit there and roll around on here, which will keep attached flow. It'll roll right onto here, keep attached flow, and prevent the tail itself from reaching a stalled condition with it. One of the other things the dorsal fin will do, it will give you a nice balance between the directional stability that the fin would be. For example, if you plotted this thing, and this is angle of yaw here, right and left, 2 degrees, 4 degrees, -2 degrees, or make it the opposite direction, right and left situation in here. What you're looking for is a nice straight plot on the thing. So that so many degrees this way you get a certain force, and so many degrees the other way you get a certain force. This is nice, but this isn't what you always get. Sometimes without a dorsal fin, your curve will actually come up and flatten out a little bit here and go over this way. This becomes characteristics of the fuselage and wing combination and several other things. But that's really not too good. When you have an airplane that sits there and it's loose in directional stability, that's the way the pilot would feel like, and then it starts to get heavy as you start to apply controls into it, you got this unbalanced, uneven forces you want to do. A dorsal fin is a very strong and powerful thing to do that. On a Yankee, that's exactly what we did. You put a little dorsal fin up on top, and it brought this curve out to be almost a linear condition from zero angle of yaw, right or left, either way, on up through. And that made the flying qualities, the handling qualities, very, very nice on it. We can talk about tail volumes here. This is sort of a rule of thumb factor in utilizing and determining the size of your tail, but it's something to really begin with. It's at least a good starter. If we talk about the tail volume of the horizontal tail, you can determine the area of the horizontal tail, S here standing for the area of the horizontal tail, which will be equal to the horizontal tail volume coefficient times the area of the wing times the mean aerodynamic chord of the wing. Divide that by the length from quarter chord of the wing to quarter chord of the tail. That distance is what LHT would be. Put these factors into here and you can get a pretty good idea of the amount of area you need for your horizontal tail. For the vertical tail, it's somewhat the same. The area for the vertical tail would be equal to the vertical tail volume coefficient times the area of the wing times the wingspan. This is the total wingspan of the wing, again divided by the length between the quarter chord of the wing and the quarter chord of the horizontal tail. When I say quarter chords, I'm talking about the mean aerodynamic chord of the wing and the mean aerodynamic chord of the vertical tail, or in this case the horizontal tail. To give you some rough idea as to what some of these coefficients would be, for an air coupe, the horizontal tail volume coefficient was 0.36. For 140 it goes to 0.49. A 170 is 0.76, which incidentally is about one of the highest ones around. An Avion had 0.62. A Bede 4 had 0.65. And a Bede 5B had 0.55. Now, this is by no means an exact way of doing it, because in this case of the Bede 5, the propeller was in the rear, so that was adding to stability, and that's not taken into account here. All these other airplanes have the engine and propeller up front. They destabilize. Therefore, if you take that into account in any of these factors in here, you would either be finding that your effective areas increased or decreased accordingly. But as a rule of thumb, as a beginning, this gives you a reasonable idea on it. When it comes over here to the coefficient for the vertical tail, you see the numbers are different, but they go from 0.028, 0.037, 0.055, 0.036, 0.45, and 0.32. Unfortunately, it's not precise. You have to take into account all the other things. But if your airplane looks similar to one of these, then you're going to be pretty darn close to coming up with the exact number. If not, you just got a good ballpoint figure to work with. I think one other area we can talk about a little bit is a flying wing and a canard configuration. These configurations actually have nothing to do with stability and control, except the fact that you do different things to handle it. But when you start to analyze the stability and control, you start to find out that a configuration can be stable, but also has some particular characteristics you have to be concerned about. One of the very best texts to use in analyzing your stability control is the book Airplane Performance, Stability and Control by Perkins and Haig. This particular text goes into the subject very deeply, very thoroughly, and in very concise manner. You can very carefully and very properly analyze in good engineering practice the stability and control characteristics of your airplane, general aviation type airplane, utilizing this text. Another good one is Supersonic and Subsonic Airplane Design by Koenig. This text is got a good bit of information on stability, control, handling qualities. It's a text we definitely recommend. And a very good one, The Design of the Airplane by Darrell Stinton. It not only has good wealth of information on stability controls and control surfaces, but a great deal of other things very applicable to general aviation and home-built type aircraft. There is one other NASA report done in 1949. It's entitled TR 927, which is Prediction of Flying Qualities, and it is an extremely good NASA report dealing into the complete subject of handling and flying qualities that you should expect out of an airplane.